All right, so this is Physics 1A, or Section 1617 for April 1st. Today we are going to do two things. We're going to talk about this energy problem over here on the right, and we're also going to discuss power and do one of those problems. This will not be a long lecture today. Since we're back to like normal schedule, that means I'm going to be lecturing on Mondays, like the full 3 hours, and then we'll do 1 hour on Thursdays, and then the remainder of the time, will just be if you have questions or that kind of thing, since it's technically lab time and we've done basically all the labs we're going to do. So probably be about an hour, hour and a half today max. If you guys have any questions in general, you can always ask. I have the chat channel that's called Physics 1A General. It's up on my second monitor, so I can very easily, answer questions that you have there, or you can, answer questions that I ask and stuff like that. So just as a review of what we did last time, we learned about how to calculate work, right? We learned that work is calculated kind of in the most general way by doing an integral of f dot dr. We also found that if we know how to calculate work for different types of forces, we can also use an equation that's related to the conservation of mechanical energy that says that if you add up all the work done by non-conservative forces, that has the effect of changing the mechanical energy of a system. And the mechanical energy is the kinetic energy plus the potential energy. In this class, that potential energy gets broken down into a potential energy due to gravity, as well as a potential energy due to springs. And we said that we could identify what each of these elements are by saying, okay, kinetic energy is defined as 1/2 mass of an object times its velocity squared. Then we said that the potential energy due to gravity is given by just mg times the y-coordinate for an object, where y represents the altitude above the surface of the Earth. And then we also said that the potential energy due to a spring we could find by 1/2 kx squared. And with these ideas all together, you can solve a lot of problems. And we're going to look at two that you can look at today, as well as talk about how we use power to address other types of problems. So this is the first one we're going to do. I guess I could put it up here. Move this one down just a little bit before we get to it. So there's our problem. Take a chance to read it and think about it. I think I told you guys last time we'd be doing this, so I hope some of you have already read it. On a thrill ride, a cart filled with people has a mass of 1,000 kilograms. I'm going to write down the information as we go through this. So that's going to be mass. We'll just say in this problem, mass is equal to 1,000 kilograms. And then it says that it compresses a spring with a force constant of 45,000 newtons per meter. So that's K equal to 45,000 newtons per meter. It pushes the cart up an incline that's angled at 30 degrees. I'm going to call that theta, so we can use theta instead of writing 30 every time. And the ramp that it's moving along ends abruptly at 20 meters. And we also know that the initial compression, I'm going to call this x sub 1, of our spring is this 2 meters right here. Okay, find the distance up the plane that the cart stops, or will the cart go over the edge? All right, we should probably draw our own picture of this over here. So we've got a ramp, and in the initial situation, we've got a spring that's compressed right here, and connected to that is this cart full of people. So here's our cart. Oops, it's hard to draw like this. And there's some people in here. And initially, we know some information. And I'm going to kind of write down all the information we know here. So we know this angle is theta. I said over there that we said that I'm going to kind of put in a little box over here, all the information we know. Within our equations for energy, these are the three variables that we have to account for: velocity, altitude, and x. So in both situations, we need to label what is the initial compression of the spring, what's the initial altitude, and what is the initial velocity of the object. And I'm calling those just v1, y1, etc. The cart starts off at rest, so its initial velocity is just 0 meters per second. Its altitude, we're going to start off as defining as 0. You can always pick whatever point you want to be 0. So we're defining this point right here to be y equal to 0. And then it's x1. This is the amount by which the spring is compressed from this equation here. And I said that's going to be equal to 2 meters. This is kind of like your initial scenario before the spring actually, decompresses. The second scenario is you've got your same ramp, and what we're trying to figure out is basically how far up the ramp the cart actually goes. So now the spring has been decompressed a little bit, and the cart's going to be somewhere up here, okay? And we don't know where it's going to be. Here, I should use the same color so it stands out a little bit more. The cart's going to be like right here. And let's just say that relative to where it started, okay, so it started somewhere back here, right? That it moves some distance along the ramp, and we just call that distance d. We don't know what it is, but we're trying to calculate what that's equal to in this case. Oops. So what is d? What's the distance up the ramp it goes? And if that distance is longer than 20 meters, then people are going to fall into the ocean with the hungry piranhas. Okay, now we need to label information about the second situation here. So again, the possible things we can have are going to be x2, y2, and actually I don't want to write this stuff here because I'll need to use that area. This will be, in this situation, it's going to be x sub 2, y sub 2, and v2. Now if it doesn't actually go over the edge, this is going to be 0, the velocity. And if the spring is not compressed anymore, then this is going to be 0 as well. So the only thing that's not going to be 0 is the y. And what we'll say is that if we draw a line like this, and we say that the distance that the object is actually kind of from back to back, right? So we go the distance to this point right here. This would be the y-coordinate of the object, and I would say that this should be equal to some d times sine theta. If this is theta, right here, and that length right there is basically d, right? Then y2, we'd say, is d sine theta right here. Okay, and ultimately that's what we're trying to solve for. We'll use this equation to do that. Before I keep going, do you guys have any questions so far? Why is v2 0? Well, the goal is to find the distance up the plane that the cart stops. So that's why v2 would be 0. How far up the plane will it go before it stops? Does that make sense? Okay. We're using that equation, right? We're going to say in this particular case that the work done by non-conservative forces is 0. We're going to assume that there's no friction, mostly because there's wheels and we didn't get any information about friction. Changing kinetic energy, that's going to be 0, but I'll write it out anyway. I'm just going to write out the entire expression. I think it's a good idea to do this every time just to make sure you don't make a mistake. So that's the change in kinetic energy, plus the change in potential energy is given by mg times just y2 minus y1, right? Final minus initial, that's what you do for change every time. And then for the change in potential energy of the spring, we'll just do k times x2 squared minus x1 squared. We can go through here and label which one of these things is going to be 0. So basically, the initial velocity and the final velocity were both 0. I think the initial height, y1, was equal to 0. And the final compression of the spring, x2, is equal to 0. So ultimately, what we end up getting is mg times y2 is equal to 1/2 k times x1 squared. That's all that's left over. You've got this term, and you got that term. This one's negative, so you add it to the left-hand side or right-hand side, whatever you want to think about it. But mg y2 is going to be equal to 1/2 k x1 squared. And then we just need to solve this. We knew that y2 was also equal to, so this is also equal to mg d sine theta. And then we can just solve for d, right? So it's going to be k times x1 squared divided by, and then there's a 2 as well. I think that's correct. That should be equal to d. And you guys can start plugging in numbers, and I'll write it on the screen here. So it's 45,000 newtons per meter times 2. And I'll pull the calculator and we'll try to calculate this. If you guys already get an answer, you can just type the answer out. If you have questions, please ask. If you notice me make a mistake, definitely tell me. 18.4. I'm pretty sure that's the right answer. That sounds right to me. I'll finish putting it in here real quick. Yeah, that's also what I got. 18.4 with a whole bunch of digits after it. So that's less than 20, so that means that these people don't actually go over the ledge. You guys have any questions? So for energy problems, there's only one thing to consider, and that's what the positive y direction is. So positive y I made this way. Oh, that's not y. Positive y I made this way. And as far as x goes, the x direction is parallel to the spring, if that makes any sense. So it's really just about the spring itself. So I don't know if that answers your question. I just said x represents the compression of the spring, so it can either be positive or negative. It doesn't matter what you choose because it's squared, right? So it doesn't matter if you put in positive or negative for x. This just means like all that the x represents in the 1/2 kx squared equation is how stretched or compressed is the spring. Okay, cool, no problem. That's something that people definitely get confused about. You know, there's a way we could make this problem like a little bit harder to be maybe a little more helpful to you. And so that's what I want to do next. I want to, here, we'll do this one later. If we have time. I know for a fact you guys have a homework problem that's really similar to this, except it's like quite a bit more difficult. I want to add in 2 things here. We'll do a part B for this. So we're going to say, what if the coefficient of, it's rolling, but let's just assume that it's like kinetic friction, okay? Or we could call it rolling friction if you want to, but let's assume that the coefficient of friction in this system is equal to, let's say 0.1, okay? I don't know why I put parentheses, just 0.1. And let's say we ask the following question. How much should we compress the spring so that when the person, so basically so that the people on the ride get right to the top without actually falling over, if that makes sense. So the question would be, does that make sense? Does that question make sense to you guys if I write it out like that? How much should the spring be compressed if we want the cart to come to a stop at the end of the ramp? Does that make sense to you guys? We have to find x1 now, but it's going to be more complicated than that because there's also friction. So what I'm going to do here to make it, so we knew it was 18 meters, right? Okay, so this is our scenario now because this is going to change just a little bit. I'll try and draw this kind of big. So our scenario now is, there's our ramp, and we know in our initial situation that we had this spring. And if you look at the picture, how far is it from the uncompressed point of the spring to the end of the ramp? Looking at the picture back here, how far is it from the uncompressed point for the spring all the way to the end of the ramp? 18, not 22, but 18, right? Because it's 20 all the way. You have to subtract the 2, right? So what we know now is that it's 18 meters for the uncompressed spring length, right? So we've got this distance of 18 meters to work with when the spring has no compression, right? This is 18 meters now. But what we're going to do is we're going to compress the spring, right? So we'll compress the spring from that point by some distance that we'll just call x or x1 or whatever we want to call it, right? So that's your equilibrium position for the spring right there. Say EQ. And now we throw our writers in here. Oh god. Here we go. So now we're going to say we compress this by some distance that we call x or x1, I guess, right? And our goal is to find what is x1 equal to exactly, as someone said in the chat. That's our goal here. What's the compression so that the person comes to a complete stop at the end of the ramp, right? So the final scenario is going to be, here's our ramp. Apologize for the drawing. They're going to be right here. Well, I want them to be exactly 18 meters, so we'll push them up a little bit here. They'll be just about to fall off or something. So they're right up here on the edge. Because I want to make sure that they actually go 18 meters. Okay? And maybe they fall off. We're not really worried about that. We just want them to get right to the edge, basically, is the point. All right, so that's our scenario. That's our problem, right? Do you guys want to take a second and try to solve it? Like, can I give you guys like 5 minutes and you try to solve this? Have I given you... Go ahead. Have I given you enough information? Do I need to zoom out just a little bit so you can see the... That was... Here, you know what I can do? I can just box this. Oops. Box this. Copy. And then paste it down here. Oop, paste it down here. There we go. This part's not going to be here this time, though, but the rest of the stuff is still the same. So now you've got all the information. Scroll down just a little bit. And go from there. So take like 5 minutes and see if you guys can solve this. And if you need more time, I'll give you more time. If you have questions, feel free to ask. Okay. I don't know what the answer is, Kenny. That's I haven't worked it out yet. I just made this problem up just now. Normally we just do the first half of this, but I realized that like thinking about the homework problems I assigned, this is probably helpful to talk about because you have one that's really similar to this. Anyone else get 1.93? Interesting. Did you guys include the compression distance into the friction force? Did you include the distance that the spring is compressed into the work done by friction? Okay, you want to try that? That's usually, yeah, that's usually what people miss. Try that again. Okay, I typed it out in case there's any lack of clarity. Please let me know at any point if my mic cuts out. I need to know if like this internet connection's stable or not, because it should be, but we will see. Could be. Should probably be greater than 2. Anybody else get that same number? Did you have to solve a quadratic? 2.6. Okay, let's work it out here on the screen, and we'll see what kind of numbers we get. Okay, so I want to emphasize something that's really important. So be sure you're paying attention. The most important part of doing these problems is it's not the picture or anything like that. It's these things that are in green here. So like this is what you need to be doing every time you're doing one of these problems. You need to be making sure that you identify the information about the endpoints of the system. The whole point of energy is that energy is conserved between any two endpoints you choose. Okay? Any two endpoints you choose. So as long as you know the information about the endpoints, you know, x1, y1, v1, that's what you should be thinking about. Okay? When you start the problem, the first thing you should do is say, okay, what's y equal to 0 going to be? All right. Let's make the uncompressed distance for the spring to be y equal to 0. Is that okay with you guys? So we'll call this point right here. This is going to be y equal to 0. All right. You know what? No, let's not do that. I just realized something. It's going to make we have to do 2 triangles. Let's not do that. Let's call the starting point for the object. We'll call that y equal to 0. So that's y equal to 0 right there. And now let's label, see if I can get this to work. Oh, it didn't work. Undo. I have to hold it, right? There we go. Let's move this up here somewhere. Over here. So we're going to say y1 is equal to 0. Right? Okay, let's put in green just like we did before what our information is. So we're going to have y sub 1, x sub 1, and v1, right? We know the initial velocity 0, x1 is the value we're looking for, and y1 0. Down here, what are we going to have? So our spring is now decompressed. I should have drawn that here. Out to the equilibrium position. But our initial location, we said, started from basically somewhere back here. And that position, we said y equals 0, right? But now we need to know, what is y final? That's y2. What's that going to be equal to? So y2 is going to include a couple distances here. Maybe I mark them off in a different color, like red or something. So the object started here, right? And it went to here. And that distance was called x1. And then the object went another 18 meters, right? Oops, 18 meters, yeah. So I would say that y2 should be equal to 18. Here, I don't want to write that part in red. Go back to green. So y2 should be equal to 18 meters plus x1 multiplied by the sine of the theta. Does that make sense to you guys? Does anyone have any questions? You need to include the total distance, basically, that it moved. And then the other 2 things are 0, right? The spring is no longer compressed, and the final velocity is 0 down here, too. You'll notice that when you do these kind of problems, that usually, like, a bunch of these things are 0. You usually don't have, like, values for everything. You usually have a bunch of zeros, pretty much. So, it is what it is. All right, so there we go. I can't emphasize enough that this process that I just did right here is exactly what you need to do in every single problem. Just like with Newton's second law, where you had to do free body diagrams for every problem, and you also have to do a free body diagram for this one, right? Because you need to calculate friction. But Newton's laws, what do? You go label your axes, draw a free body diagram, use Newton's second law, right? This is very similar. You pick an axis for y. That's all you care about is the y-axis, up and down. You pick a point for y equal to 0, and you just go from there. You label y1, x1, v1, and then y2, x2, v2. Does that make sense to you guys? That's how you do these problems. There are other ways that people can teach you, but as I've tried to emphasize in Physics 1A, this class is about learning the methods that always work, and this method will always work, okay? So if you try to do it another way, if you try to take a shortcut, you might miss something. You might get it right, too. Just saying, if you do skip steps, you should expect that when you go back and do the problem again when you miss it, you should stop skipping those steps. And this is the step. You do that, then you do this, and you fill out the information. In this problem, we do have work done by non-conservative forces, right? Because there's friction, right? So I'm just going to label, I'm going to do this one step at a time. Work done by friction is going to be on the left-hand side. We know that the change in kinetic energy is 0 because the velocities are 0, so we don't need to write that one again. For UG, we've got mg, right, multiplied by just y2 minus y1. And again, I'm not going to start plugging things in instantly. I'm going to make sure that I don't forget something. Everything that we do here is like a, what's it called? It's a to-do list or something like that, right? Like you go to the store and you have your to-do list and it says you need to buy eggs, you need to buy coffee, and you need to buy, I don't know, spaghetti or something like that, right? You go there, you do those things, then maybe you buy some other stuff too, right? This is your to-do list. Your to-do list is do this, write out the equation, and then this equation, it reminds you, okay, I need to put in y2, and I need to put in y1, and that's where you go back and you use the information, right? Like I said, you can skip these things. It's just, if you get the problem wrong, what I'm always going to tell you is go back and don't skip steps, because that's how you get this stuff right. It took me forever to believe this, and I reiterate it over and over again to you guys because it's probably going to take an entire semester before some of you start believing me. Maybe some of you already do believe me, and that's great. But if not, just trust me. Don't skip steps. It will make your life easier. Okay, work done by friction. That's the force of friction, which is mu mg cos theta. This should be, I hope, something you remember how to do. I did it while you guys were working. I'm sure that you guys already know how to do that. We also need to multiply this by, oh, I already put the negative sign in there, but I'm going to take it out for a second and talk about why it's there. We need to multiply this by the distance that the object travels, and the distance the object travels is this, right? That's how far it moves. That's how far it's going to feel some kind of a friction force. So 8 meters plus x1, that's right, 18 meters plus x1. And we also need to multiply this by another cosine of the angle between the displacement vector, which went this way, right? That's like your, I don't know, you call it delta r or something like that. And the force of friction, which points back in the opposite direction, right? And so the angle between these two is 180 degrees. So don't forget that, like, this can confuse people sometimes. Like, there's a cosine theta here, but it's from Newton's laws. It's not from, you still need this one here. So that entire expression is the work done by friction. And then on the right-hand side, we have some things that drop to 0. We said that, x2 is 0. And I think we made y1 0, right? So we have, on the right-hand side now, only 2 terms remain, which is going to be mg times y2. Is it okay to put in y2 now? Not yet. There's some numbers in y2, so I'm waiting to put that until the end. Although I did put this number in here. I guess it's okay. Yeah, we'll do mg times 18 meters. It's a really bad 8. 18 meters plus x1, and then this is times the sine of the angle, theta. And then plus, I'm going to move these guys over here again. And we go plus no, it's minus, right? Because this symbol here is minus. It's going to be minus 1/2 k x1. So there's our equation. And we see that we've got x1 squared right here. And we've got x1 to the first power here, and we've got some terms like this one that have x1 to the 0 power. And that's why we have to solve the quadratic here. So it's obviously like a bunch of numbers to plug in. Man, this is going to take a little bit. So this is negative. We've got, let's just what I'm going to do. This is what I usually do when I have situations like this. We've got something times x1 squared. Put that at the very end right here. That's negative 1/2 k. Then we've got a whole bunch of stuff times x1. Leave some space for that. I don't know if that's enough. And then we have a bunch of constants. Okay, so the constants are terms like this one, but it's times this, this is negative 1. So if I add it, if I want this to be 0 on the right hand side, I'm going to get this. I'm going to get mu mg cos theta multiplied by 18 meters. But over here you notice that there's another like 18 meters times sine theta mg. So what I'm going to do is I'm going to say, nah, never mind, we're not going to do that. We'll just say this is times 18. And then we have a plus, there's this term, mg times sine theta. Oh man, it's starting to get bad. Sine theta, I have to erase this. Multiplied by 18 meters as well. I think that's it. Plus some stuff times x1. And the stuff times x1 is going to be like a lot of the same stuff here. So it's got mu mg cos theta times x is going to show up in there. So it's going to be mu mg cos theta. That's times x1, and then there's plus just mg sine theta, I think. Yeah, this expression appears twice. It'd be worth our while to actually calculate what it is, but there we go. That's basically our equation. I kind of want that all to show up in black. So what I'm going to do is okay, do you guys have any questions? Did I make any algebra errors there? Can we just calculate what this number is real quick? It's just a number, right? And it shows up twice in our problem. So I'm just going to calculate that using the calculator. I think I can. So we said mu is equal to 0.1. And we're multiplying that times cosine theta. So for that I have to put 30 and then click cos. And we're adding to that sine theta, which is 0.5. And all of that we're multiplying by mg. So that's what? What was m? Was it 1,000? Oh, it's 1,000, yeah. $5,748 is what that number is. So this is 5,748. The units are going to be newtons, actually. Oops, not that. This one. 5,747. So it's actually like, we're like, let's call it 5,750. Oops. No, I shouldn't do that. It's 5,748. Okay, so that's times x1, and then minus 1/2 of k is going to be 22,500, I think. And then this is going to be plus, this whole expression here is the same thing times 18. So if we take that number that we just got and we multiply that number times 18, that should be our other, so 103,477. Okay, that's my final equation there. Do you guys agree with it? Using commas as placeholders for those of you guys that are used to these as being decimal places. Is that okay? Does that look okay to you guys? Maybe you worked it out yourself while I was talking. Do you get the same answer? Did I make a mistake? I'm gonna check my algebra here. Can you guys put that in the quadratic and tell me what you get? Right, this should be 5,749. It's not it's gonna matter. Wait, what's up?
You got 5,7, you said?
No, I don't know what the answer is. I didn't do that yet. I'm just checking my work. This should have been a 9, though. You guys agree with the equation, though? Does it look like the math's right?
So, you take the work done by the friction as positive?
No, it's negative. This right here.
Oh, it is negative?
Yeah.
Oh, okay. Oh, there we go. Okay, there's that minus.
And then I added things, like I added this whole expression to the right-hand side because it's negative on the left. So that's this. Mu mg cos theta times 18. Oh, there should be a mu on this term too. Oh, no, because it came from here. My bad. No, it's good. It's mg sine theta times 18. And then they're both exactly the same, right? Because you have 18 plus x over here and you have 18 plus x here. One is sine, one is cosine. No, it looks right to me. Okay, we're just going to throw this into Andrew Elliott's typing. Did you get an answer, Andrew? Throw this into the quadratic. 2.27 and negative 2.02. Yeah, 2.27. Wasn't that one of the answers somebody else got? We got a 2.39. It shows you how hard these problems are, actually. It's not that much different than what we did, but the like calculations or the algebra or the arithmetic or whatever you want to call it, it's just a little more intense. I mean, a lot of this stuff could be shortcutted if I just calculated the numbers in advance, but it's whatever. You guys agree with that? So you say 2. So the answer is going to be 2.27 then. The negative answer is not. The negative answer means something, and I can talk about what it means in a second, but I don't think it actually is going to represent anything. So we get, as a final answer, we get that x sub 1 is equal to 2.27 meters, or negative 2.02 meters. And this is going to be our answer. We'll talk about the negative, what it means. Do you guys have any questions about that? I'm virtually certain there's a homework problem you guys have that's identical to this. Almost exactly the same question. But I think you have to find D instead of X or something like that. One of the two. I just know when the compression of the spring is unknown, these problems get really hard. And some teachers won't give these kind of problems for some reason because they think it's too hard for the math. And I don't know. I know you guys are good at math. I'm sure you can handle this. It's not that hard, right? You just got to organize the information, right? Just to go back through and repeat what we did. You label what's going on at the endpoints, right? If you want to, it's the setup, Daniel. That's exactly right. You just set it up properly, and you let the history of physics carry you through, which is the conservation of energy idea. Take your time, go slow. it's worth it to get it set up right before you start going through it. You know, because if it's not prepared properly, then you'll make a mistake later down the line, and you may be looking through your algebra and being frustrated and anxious, and dealing with all the other stresses you have going in your life. It's not going to be easy to figure it out. The negative 2.02 here. Let me talk about this for a second. I think this means this would also work if the spring was like out here. Like if instead the spring was out somewhere like here, not quite, but like it was already expanded a little bit, I guess you might say, or decompressed a little bit. I think that's what this represents. I mean, it should, right? Because then this number would become, you'd have a smaller rise. Like you go only 16 meters is how far you would go. So there'd be less work done by friction. I guess that's another way to get it to work too. So anyway, do you guys have any questions about that? I feel like that's about as hard as energy problems can get. I think there's an exam up that I gave a few years ago that is a problem like this, except that I added in something where like the thing launched off the edge and had to land on a platform or something like that, which made it a little more tricky, but it's about as hard as they can get. So last topic, we're not going to take a break. We're just going to go through in maybe another 20 or 30 minutes, but that's going to be the end of the thing. So just bear with me for a second. If you do need to take a break, then that's cool. Let's talk about power. And this should give you all the info you need to solve the rest of that assignment. Again, just to remind you, I did extend the homework that was due tonight. All right, so this is the power, is the rate of energy consumption, or it's the rate at which work's done. It's either the rate of energy consumption or production. So the rate at which something's giving off energy or taking in energy, that could be power. Like a light bulb. A light bulb, and power is measured, by the way, in watts. And 1 watt is equal to 1 joule per second. We have another measure of power, which is the horsepower, and 1 horsepower is equal to, I think, 746 watts. And it's also equal to 5,500 or 550 foot-pounds per second, I think. We need all of these things. I need to go look this up. I didn't look this up before we started class today, and I take for granted the information that's available off the top of my head. So I'm just going to really quickly here see what 1 HP in watts is. 746, okay. And if we do, let's see, 1 HP in FT LB 550. Okay, I got it right. Yay. Okay. So those are our units that we use for power. It's the rate of energy consumption or production. It could also be considered to be the rate at which work is done. So there's 2 different symbols we can use for this. There's average power, which is kind of equal to like work done divided by time. And there's also instantaneous power, which can be thought of as basically being kind of like the rate of change of work with respect to time. It can also be thought of as the rate of change of the mechanical energy of the system with respect to time. Energy E, when I write that symbol, is equal to mechanical energy, which is kinetic energy plus potential energy. This would be like instantaneous power. Now there's another way we can write it though. If we replace the if we think that the dW here can be replaced with something like, I don't know, let's say like F dot dr from our original equation we started class with today, which is that work done is equal to the integral of F dot dr. So if we write it like this, then we can say that this power equation can be written as basically F dot dr, and then we put the dt down here. And then this allows us to write it as F dot, because dr dt is the rate of change of position. So this becomes velocity. So this is another way we can find power. Force dot product with velocity. This one's really useful, as it turns out. Often much more useful than these other definitions. Okay, that's power. Do you guys have any questions? What does power mean? If I tell you that I've got an engine that has a power rating of 2 horsepower, and I've got another engine that has a power rating of 1 horsepower, okay? And let's say that each of these engines is used to mow a lawn or something like that. The one that has twice as much horsepower can complete the job of mowing the lawn in half the time that the 1 horsepower engine would take. Does that make sense? So 2 horsepower versus 1 horsepower. Double the power means it takes half as much time to do the same amount of work, pretty much. So things can get done more quickly. In terms of a car, more horsepower means, the car is more powerful. It can have a faster 0 to 60 time, right? It's more force is available to generate more kinetic energy for the car. So that's when we say, a car has a lot of horsepower, like a muscle car or something like that would have 500 horsepower. Then you compare that to like a Honda Civic. The car that has more horsepower can get from 0 to 60 miles an hour very quickly, whereas a Honda Civic is going to take 12 seconds or something to get from 0 to 60 miles an hour, maybe. Maybe I'm exaggerating, but that's kind of the idea of what power is. How quickly can you convert energy into kinetic energy, for example? Or how quickly can you convert, how quickly can you raise something? That would be another example of power. Is like you're lifting an object from the bottom of a quarry, like you've got some rocks that you're digging up in a quarry, and you're going to lift these rocks up to the top. How quickly can you get the rocks to the top, right? And if you have twice as much power, you're going to get the rocks up faster. Does that make sense to you guys? It's how we take energy and incorporate time. That's pretty much it. So let's use this idea to solve this problem right here. So, a different color. So it says a car engine has a output power of 20 horsepower. So we'll just say power out is 20 horsepower. When the car is traveling at a constant 55 feet per second on a level road. So when the velocity of the car is 55 feet per second. We want to find the average drag force acting on the car, and then some other things. So the first thing we'll do is to find the drag force acting on the car. To do this, we kind of have to draw a picture of what's going on. We've got a car that's traveling along the road, and it's being pushed forwards by its wheels, right? But I'm just going to say that we call this the force of the engine. There's going to be a normal force acting on the car that points up, and there's going to be a weight acting on the car that points down, and then I'm going to say acting backwards on the car, there's going to be some kind of a drag force, right? So here's our car, and those are the forces. The main two forces we consider here are the engine force, which goes this way on the car, and the drag force, which is pulling back this way on the car. So, in order to find what the drag force is, we can just use this equation right here. This equation says that the power is related to the force times the velocity, right? And what we have here is the power and the velocity. So if we take power equal to F times V, then we can say that the force, in this case, which I'm going to say is the force of the engine, it's the engine that has the output power, right? So it's the force of the engine, should be equal to the power output divided by the velocity of the car. The power output is 20 horsepower. We want to divide that by 55 feet per second. That's going to give us the force of the engine. But if we think about what's happening, if the car is moving with a constant speed, what does the net force acting in the car have to be equal to? 0. That means that the engine force is basically equal to the drag force. This is how it works. You're driving along the road. You need to put power into the car to actually keep it going, right? You can't just coast at 70 miles an hour down the road, right? You need to put pressure on the accelerator to keep the car going, assuming you're on a level road. If you're going downhill, maybe that's not the case, right? But your accelerator's on, so there's power coming from the engine, but the drag force is kind of there to kind of balance it, and that's how you end up moving at a constant speed. If you want to speed up, go faster than 55, you need to increase your engine output power, but that's also actually going to increase the drag too. Okay, so we can't just exactly solve this, because if you look up here, horsepower and foot-pounds per second they're not one-to-one, right? It's not like, it's not like Newton and, kg meters per second squared. These are equivalent, right? But horsepower, there's a conversion factor, right? So we actually need to multiply this by a conversion factor. Let's see that real quick. So we want to multiply this by, we want to convert the horsepower. So we'll say 1 HP is equal to 550. Oops, I didn't write that out right. It's foot pound over seconds. There we go. The 55s cancel out. I think we end up getting what? Let's see. 55 and 55 canceled. So this ends up being 100 times 20, which would be what? 2,000? Did I calculate that right?
Oh, is it 200?
It's 10 times 20. Thank you. So bad. So bad. 200, and the answer is actually going to be in pounds, right? You can look at the units. You can see the feet per second, the feet per second cancel. So we're left with just 200 pounds. And then this, as we said over to the right, is also going to be equal to the drag force acting on the car. Does that make sense to everyone? Okay, part B, things get a little trickier. In part B, it says, if the drag force is proportional to the speed, and the speed doubles, find the power needed. If the drag force is proportional to the speed, and the speed doubles, find the power needed. So when they say that the drag force is proportional to the speed, that's like saying that there's some constant, maybe we call it k, that if we multiply it by the speed, that's going to give us the value for the drag force. We don't necessarily know what this is, but we could technically calculate it if we wanted to. The other thing we know is that the power from the car is equal to the engine force multiplied by the velocity, right? Now our goal here is to find the power needed, right? So this is ultimately what we're trying to calculate, is what is P, right? We also know from the previous part that the drag force happens to be equivalent to the engine force when the car is traveling at a constant speed, right? So we can kind of combine these together here, I believe, to say that Fe is equal to drag, and drag is equal to kV, right? So I can replace Fe with just k times v. So this is going to become k times v squared. Oops, k times v squared is equal to the power. Now there's two different ways we can solve this. For this problem, I can't remember which is better. We can either find the value of k, or we can set up a ratio if we don't know what k is, right? We'll do this both ways just so I can show you. The power of ratios is strong. This equation tells us that power is equal to some constant times velocity squared, right? So what I could do is I could say, suppose that we say power 1 and v1. So if we know, for example, p1, if I use the information from the first part of the problem, the power in the first part was 20 HP, right? And the velocity that came with that power, I think, was 55 feet per second, right? So I've got those values, right? And if I divide this by another equation where I use the power for part 2, we'll just call it P that we're looking for, and I say that's equal to the same constant K multiplied by the velocity 2 squared, right? And we know that the speed is going to double, right? The speed doubles. Here, I don't want to call it V2. I just want to call it V. That means that our velocity V that we're looking for, that we're using here, is going to be double V1, right? So it's 110. 110. And we can use this to find power, right? Because if we take the ratio, then we get that P1 times V squared divided by V1 squared ends up being equal to the power that we're solving for. And if we do that, then we use the values from the first part. So this part, if we do it this way, we don't even need to convert. So we'll do 20 horsepower, and we'll multiply by V, which is 110. We got to square that one. And we divide by 55. We got to square that one too. I'm pretty sure this is basically like 2V over V, the squared, so it's going to be 4. I think it's going to be 80. Do you guys understand what I just did? We'll do it a different way too. Did that make sense to you guys? Stop for a second. Yeah, sure. I can go that again. So we've got this equation, right? That tells us that power is equal to k times v squared. So if I have a situation where I have some P1 and V1 that are coupled to each other, and I have a P2 and a V2 that we know go together, okay, then I can make a ratio. I can say, okay, let's do P1, V1, P2, V2. I don't care what they are, I'm just talking about how equations work now. These cancel, and we just get P1 over P2 is equal to V1 squared over V2 squared. You guys do this stuff in chemistry all the time with this equation, PV equals nRT, right? It's exactly the same thing that we're doing here. You have two different states when you use this. Here we have, that's P2. Did that make sense, Daniel? Yeah, so it's just this, we have this constant ratio, right? Now the other way to solve this problem, which might be more useful in certain situations, is we saw before that drag was equal to K times V, right? Well, we know that drag in the first problem was 200 pounds, right? We solved for that. And we knew that the velocity in the first part of the problem was, I think, 55, right? 55 feet per second. So that means that K is equal to drag divided by velocity. Yep. And so it's going to be equal to 200 pounds divided by 55 feet per second. I don't know why I'm writing at an angle like this. This is kind of weird. So that is 200 divided by 55. This is 3.6. So the drag coefficient is, this is often referred to as the drag coefficient, 3.64. And the coefficient's actually going to have units here. No, not D. Sorry. K ends up being equal to 3.64. And you can see the units from here. That's going to be pounds divided by feet per second. And now if you want to find power, we said, right, where was power? Right here. There's our equation. Power is equal to K times V squared. So if our velocity now is doubling, we take 3.64 for K, and we multiply by the velocity V squared, which is going to be 110. We want to figure out the power when the car is moving twice as fast. And this should give us the same answer that we got before, I hope. I mean, it has to. We're effectively doing exactly the same thing. We get 44. Oh, it's different, but I'll show you why it's different. The answer you get for this one is 44,000. It's about 44,000. We'll just call it 44,000. And the units are going to be, if you look at the way the units work out, one of these feet per second cancels out, and you're left with foot-pounds per second. Now before we had gotten, let me zoom out just a little bit. Before we got 80 horsepower, right? But 80 horsepower, here, 80 HP, if we multiply that times 550, which is the ratio of foot-pounds per second over HP, should be the same number, I would bet. 8 times 5 is, 44 to 4. Yep, it's gonna be a lot of 4s. 80 times 550, so you get, same thing. This is the same thing as 44K. We'll say 44,000, running out of room. Does that make sense to you guys? We have one more part to do too. The last question is, if the maximum engine output is 150 HP, find the maximum speed for the car. I'll rewrite that down here. So if the max power is 150, then what's the max velocity? And this is where I really think the ratio makes the most sense. We don't need to do any conversions or anything like that. We just know from earlier in the problem, if we take P1 equal to, the power from the first part was, 20 horsepower? Yeah, 20 horsepower, and the velocity was 55 feet per second, right? So if we do 20 horsepower corresponds to a velocity that we call 55 feet per second, right? Then we make a ratio, just like here. We say P1 over P max is equal to V1 squared over V max. We get an equation then that says that P max is just equal to, what's it going to be? P1 multiplied by V1 over V max. Again, as I get down to the bottom here, I'm tempted to right sideways. I'll try to stop doing that. So P max then ends up being equal to, the first power was 20 HP, and we multiply that by, oh, I did this upside down. This is wrong over here. Sorry about that. Oh no, we're getting that thing where I can't. Okay, well, it's easy to fix. Just delete this. Sorry, solving this over here, the P max would go to the right side, so the V max would be the one in the numerator. So this is going to be V max over V1, and they're both squared. Oh, we're solving for V max. Boy, I'm being really sloppy right now. Here, let's fix this. This is what we're solving for, velocity. So we'll get V max squared should be equal to V1 squared there we go. Yep. V1 was 55. We're multiplying this by P max, which is 150. We're dividing this by 20. This one is still squared right here. So our answer is going to be V max is going to be the square root of whatever all that stuff is. And there's another error here, which is the, I don't know where that unit came from. This should just be feet. There we go. 150? Is that the answer? Mm-hmm, 151, that's what I got too. Not meters per second, Zeke. No. What is it doing now? There we go. Feet per second. There we go. You guys have any questions about that? This problem is just kind of all about how power is related to velocity. There's other power problems that we can do. Maybe we do them next time, but there's a few more on this page. They're pretty interesting. You're going to see examples of problems like this on your homework, the one that we just did, as well as situations in which the object's traveling uphill. But ultimately, they're not that much different. Okay, I'm probably going to stop the stream for today. I will stick around if you guys have questions. I'll be happy to answer them. Let me know about problems you're having with homework. The one that's, I think the Newton's second law one is due soon. You should be able to get started on these energy problems. If you have any questions about the lab manual problems that you have due in a few weeks, let me know. Well, that's it for today, though. I'm going to stop the recording.